session with the next talk by Del Zotto, and he's going to talk about recent progress about 5D conformal concept.
Thank you. First of all, thank you very much to Giulio and Alessandro for pushing this fantastic workshop every year. It's a pleasure to have an occasion to come back to Trieste and to meet with this wonderful crowd. I was very undecided about what to talk about, but I decided to can I erase this? Have you make a mental note of this? I was undecided about what to talk about, but then, viewing the topics of various talks and seminars, I decided to focus on more geometric type of application in the context of geometric engineering and the problem of classifying higher dimensional conformal systems. So, I don't know how much of this audience is familiar with it, but for sure at least half of it. So for that half, apologies, but let me speak to the other half. The idea is that, so have symmetries of quantum field theories, there are supersymmetries of quantum field theories, and there are conformal symmetries of quantum field theories, and sometimes we can combine conformal and supersymmetry. And that happens because of miracles in representation theory. Essentially, the exceptional isomorphisms between Lie groups of low ranks are responsible for the existence of superconformal groups. This was the reason why NAM was able to classify them, and to show that superconformal field theories exist in dimension less than or equal to 6. And then, people have constructed them using various techniques. Oftentimes, one studies the word volume theory on a membrane in a higher dimensional string theory to construct these examples of higher dimensional CFTs. And one has lists, so we have in D equal to 6, one can have 1,0 superconformal symmetry, 2,0, 3,0, and so on. In D equal to 5, this is kind of unique. There is only n equal to 1. In D equal to 4, the pattern continues. One has n equal to 1, 2, 3, 4, and so on. And it goes on in lower dimensions. So with the more fancy techniques, one can show that using the representation theory of superconformal algebras, if you want a stress tensor, then this theory stops. If you want a conserved supermultiplet containing a stress tensor, then you have these two amounts. And then by circle reduction, you see that 2,0 goes to n equal to 4, and the 1,0 will just go by total reduction to n equal to 2. Here there is a putative n equal to 2, which is the circle reduction of 2,0, but the ultraviolet completion of these theories is in this dimension, in one dimension higher, so they don't really count as superconformal system in 5 dimensions. In this context here, there is a very simple classification, goes by ADE, and these are the finite subgroup of SU2. And this is essentially due to work by Witten in the 90s. These are the obtained from type 2B superstrings on these ADE singularities. And then by circle reduction and twists, one gets to an A, B, C, D, E, F, G classification of n equal to 4 theories that corresponds to simple Lie groups. No? And one is left with these lower supersymmetric examples, like 1,0, n equal to 1, n equal to 2. Is there a classification for these? Can we hope for classification of these? No? And in this context, in the context of 1,0, generalizing from type 2B to F theory, one obtains F theory on bases which are subgroups of this type, of this type, where gamma is now a subgroup of U2, a finite subgroup of U2. And there is a classification of theories basically modeled on this. But there is also another approach, which is the so-called atomic classification. And this is an idea that was developed by I think, let me think, Heckman, then there was Morrison, Rudelius, and Vafa. About, I don't know, 8-9 years ago, they performed a classification of 6D 1,0 CFTs in terms of these atoms. And what is the idea? The idea is that one can organize this collection of superconformal field theories in terms of simple ones and some operation that you can use to start from the simple ones and build more complicated ones. No? So you start from some simple atoms, and you study their chemistry. No? So the type of bonds that this atom can form. No? And now the idea is that these atoms can be given types. And the type of an atom is essentially a collection of its flavor symmetries, if you like. So a list of Lie algebras such that they don't appear as gauge groups of these theories in some gauge theory phase. No? And in 6D, one finds out that essentially there are atoms that are just bifundamentals of this type, G1, G2. And out of these and this chemistry, so fusing them, I don't know, maybe identifying some common factors, say G2 with this G2, and coupling it with some gauge group, can form these molecules and build quivers. And the structure of the quiver is parameterized by the resolution of this type of singularities. Here's the Brochian resolutions. Okay. So one can ask, is there a generalization of this? Like this is a nice idea. No, it's a different angle. If I want to look to this collection of CFTs, most of them are non-Lagrangian, very hard to handle. And so, like, maybe there is an atomic classification that works in other dimensions. And last year, 2 years ago, I think I spoke at this workshop, and I discussed that indeed, if you think about D equal to 4 and equal to 2, you can think about the class S construction as some sort of an atomic classification, where the atoms are the fixtures, the spheres with 3 punctures, and then the fusion operation comes from gauging, and out of them you can build all of the class S theories, and maybe with some deformations and things like that, you can reach also Argyres-Douglas points. So there is some sort of a meta-atomic classification in that context. And so one asks, okay, that's this amount of supersymmetry. This is 8 supercharges. Maybe there is a way of classifying theories with 8 supercharges exploiting this atomic technique. No? And in this series of papers, we consider the case of D equal to 5 and equal to 1, which is also 5 DCFTs with 8 conserved supercharges. Okay. So, what is the spirit? Again, we want to identify atoms and we want to understand their chemistry. No? And so, the main tool that we are going to use in this context is geometric engineering. And we will see that the way in which we can engineer these models is by studying M theory on specific types of singularities. No? This is, I have to mention it before I erase their names. This is based on a series of work. It started all with a work with Mario De Marco, Michele Graffeo, and Andrea San Giovanni. They are all formerly related to SIS in some form, no? And maybe Andrea was really Trieste, no? It was related to the Trieste system, let's say. And then this work attracted our work attracted the attention of Julius Grimminger, and with him we studied the Higgs branches of the conformal matter system that we had constructed using geometric engineering here. And then it also prompted the question: are these all the ones that we found in the first paper? Are they all possible atoms that we can form? Are there other ways of building atoms? And together with Bourget, Grimminger, and De Marco and San Giovanni, we came up with a technique that like kind of allows us to get a full classification. And I will discuss this today. And then one can ask, okay, in the case of 6D, the atoms that we get are always of bifundamental type. They are labeled by choices of 2 flavors. And the 5D conformal matter that we had constructed were of this kind as well, no? Type GG or GG prime. No? One could ask, are there other examples? Like in the class S example, there is the famous TN theory that has a flavor symmetry which is G to the cube. No? So are there trinions? Or more generally, more theories with more complicated flavor structures. And this is a topic of a follow-up work that I'm writing together with De Marco, Graffeo, and San Giovanni. And yes, there are trinions. but they have a very they have a very and I'm gone, no? I'm following the trinions. But so there are trinions, but they have a very different chemistry in 5 dimensions with respect to 4 dimensions. So the trinions of type A have the same chemistry, but the trinions of type D and E, type D are very hard to find, and they have some sort of a chemistry, but not that rich. And the trinions of type E, like as we look at very hard, and they don't seem to be there in 5 dimensions. And I will discuss a possible explanation of this remark from 6 dimensions. So yes, what is the idea? The idea is that we want to find we have these atoms, and we introduce this notation for them. It's an atom. And out of these atoms, we want to perform. Well, we want to understand, like, if there is an operation which is like the analog of gauging, no, in which we take these two flavor symmetry, we fuse them, and we form a molecule in terms of a generalized quiver, no, that can be described with a gauge theory phase that has a generalized quiver of this type, no. So these are atoms. This is like a molecule, no. So let me first remind you how it works in the context of geometric engineering. Maybe a quick reminder about geometric engineering in M-theory. Okay, so what is the idea? I mean, we all know in 5 dimensions the gauge coupling is dimension full, no? So for a long time people believed that gauge theories in 5 dimensions didn't exist. They just flow to free theories. They are not the term corresponding to the action of Young and Mills, no? This term is a relevant deformation. This quantity here wants to grow to infinity when we flow in the infrared, and so G goes to 0 in the infrared, no? So for a long time, people thought that these theories didn't exist, no? They were just free theories. But then, like, Seiberg had an insight, which is that there is maybe an ultraviolet fixed point of which this term is just a relevant deformation, no? And this is also related to the fact that the instanton density in 5 dimensions gives rise to a U1 current that is associated to just this one form. This one form is conserved, so whenever you have some gauge symmetry in the game in 5 dimensions, there is also a conserved current, and this deformation turns out to be a deformation with respect to the multiplet that contains this current. No? So then, well, this is just a naive arguing. You can maybe studying some effective field theory on the Coulomb branch. You can identify some consistency condition maybe on the prepotential gauge theoretically that describes when these fixed points exist based on the positivity of the metric on the Coulomb moduli space. No, this is field theory, but this is yes.
I mean, you are always thinking about the supersymmetric case. I mean,
yeah, 5dn equal to 1. Yes.
Yeah, are there cases of UV fixed point in non-supersymmetric?
It's a very good question. A very good question. I don't know the answer. I don't know a construction in theory. So there have been some conjectures about it, and maybe some people in the audience can have more educated opinions about that. Yeah, Theo. But I don't know. I live in supersymmetric in the supersymmetric context for this talk. It will be very interesting to understand whether what we say has some non-Suzy-Dash, but let me just stop there. I don't know. That's the most honest answer. So the idea is, okay, you start with this. This is the field theory perspective, no? But then this is just consistency conditions. These are necessary conditions. You have a positive metric on the Coulomb branch, but can you argue that the CFT exists? And to argue that it exists, you need to have a dual construction in M-theory on some canonical singularity. And the idea is that if you can find a singularity such that it gives rise to a gauge theory phase of this kind, then you can say, okay, like there is a fixed point, I can construct it in M theory, and I can also realize this deformation geometrically. How do you do that? The idea is that a gauge theory phase just corresponds to a Calabi-Yau threefold, no? That has a compact rational curve, which is the locus of one of these C2 mod gamma ADE singularities, no? And then the size of this P1 is just corresponding to the inverse of the gauge coupling, and the structure of the vibration of this singularity determines what is the gauge group. No? So this is not a singular phase. No, this is a resolved phase. And this is consistent with this idea that there is a deformation that you have to do. No, so the picture of the moduli space is that you have some sort of a cone. There is the CFT point, and then you start performing resolutions of the singularity, no? And you have some Keller cone of some resolution of the singularity. Let's call this the singularity, and then like this cone here maybe is a given blow up of the singularity, no? This type where you resolve it, but then like you know that. We are in M theory, and so we can allow for flop transitions. And so there may be another cone here, another Calabi-Yau. Say x tilde, let's call this 1, this 2, no? This also goes down to x, no? Then there is another one, no? And this structure here is called an extended Keller cone in geometry. So this is an extended Keller cone. And it parameterizes the Coulomb branch of the 5D CFT of interest. No? Is the origin of the Coulomb branch, and then what happens? The idea is that if I cross one of these internal walls, what indicates these walls is just a flop transition from a Calabi-Yau to another. So typically there is a P1 that goes to 0 size, no, along these walls. When I take an M2 brane wrapping this P1, I have a particle, a BPS particle, that becomes massless. And so the effective action that I have written here for a given resolution here has to be modified. No, I have an effective action for every resolution. No, it is given by the tripole intersection numbers of the Calabi-Yau, and they jump because when I cross these walls, I have to. There were some particles that were massive. I had integrating them out. When I cross the wall, the particles become massless. I have to add them to the effective field theory. No? So in particular, funny things can happen across this wall. For instance, I mentioned that the instantons in 5 dimensions are BPS particles. Instantons are field configurations of codimension 4. So in 5 dimensions, they have a word line. They are like particles. And along this wall, so an instanton can become massless. Very, very crazy stuff happens in 5 dimensions. No, instanton become massless because the size of the instanton is controlled by the gauge coupling. The gauge coupling can go to infinite size. No, and so you have these transitions. And this is the reason why the physics of gauge theories in 5 dimensions is so different from the physics of gauge theories in 4 dimensions. No, yes.
Are your theories of a circle? Like are these parameters complexified?
Not yet, no. Here they are just real parameters. Yes.
Is it a coordinate along the cone direction, or is it a coordinate in the, let's say, information?
So this is a there are Keller moduli in this space, and the Keller moduli correspond to both mass deformations and webs for the 5D CFT. And so this you should think about this cone as being parameterized by the Keller moduli of a given resolution. And when some of the curve undergoes a flop transition, that's the locus of this wall within the cone. No, each of these is conical because you start from a singularity. No, but it's not enough to use just a single threefold to describe the moduli space of the 5D CFT. You have to use all the flop equivalent ones. And then you have this extended Keller cone picture. So each of the cone is one Keller cone, but then there are the flops. No? And what happens on the sides? On the sides, it can happen that a divisor shrinks. These are threefolds, so these are four cycles, holomorphic 4 cycles that shrinks. And when that happens, you see, you take an M5 brane wrapping one of these, and you have a BPS string that become tensionless. And this is a hard wall. Cannot cross. No? And in particular, the existence of these hard walls is the reason why, like, for a long time, people thought, for instance, that 5D quiver gauge theories didn't exist, exploiting the positivity of the metric. Because if you have a 5D quiver gauge theory, you can tune some moduli in such a way that the metric becomes negative. But what was discarded in this analysis was that there are these hard walls, and there is a BPS string that becomes tensionless before you hit the problematic region of the moduli space, and so that region is excluded. So this was realized by, I think, by the existence of these hard walls was crucial in the analysis, an analysis of field theoretical analysis by Jefferson, then Kim and Bafa. No? You have like, it's like, think about n equal to 4 super M mills, no? You have, say, SUN, you go on a generic point on the Coulomb branch, you are here, no? And then you can tune it in such a way that there is a subgroup of SUN which enhances back to be a gauge theory, like SU2 inside of SUN, no? That's something that happens on a hard wall, no? In this context, no? It depends. No, there are strings in the 5D theories. There are strings. No, the monopoles in 5 dimensions. Monopoles are field configuration of codimension 3. So in 5 dimensions they are strings. No, so whenever you have gauge symmetry in 5 dimensions, there are magnetic monopoles which are BPS strings. And when you are in a gauge theory phase like this, no, then you have shrunk all the device, all the curves corresponding to this singularity. You are left only with the size of this P1, but in particular, all the monopoles are tensionless here, like, because you have shrunk all the, no? And so along these hard walls, you find some gauge theory phase, some partial gauge theory phase, for instance, as an example, or some partial CFT, like some smaller subsystem that becomes super conformal only along this wall, and then the whole thing becomes super conformal only here, no? And then the idea is that at the origin here, no? So this is the Coulomb branch. And then here at the origin, you can open a Higgs branch. And then you can have mixed branches, no, that go all the way, no? And the idea is that we say the Coulomb branch corresponds to this extended Keller cone. The Higgs branch morally should correspond to deformations of the singularity, no? Now there is a question because this picture is schematic, and in principle one should tell me, I give you the algebraic geometry for the singularity, I tell you how to resolve it, how to deform it a little bit, no? But in principle, to give you an M-theory solution, I should give you the metric, no? And in the context of compact Calabi-Yau's, there is the Yau theorem that says that there is always a metric in that Keller class, no? But if the Calabi-Yau is non-compact, like here, the metric exists, but is not necessarily unique, no? And so there are many subtleties that happens in the physics of 5-dimensional field theories. Like, for instance, for a given metric, you might find a theory that confines. For another metric, it doesn't. And like, there are very interesting. It's a very interesting and rich physics that needs to be explored. And we know very little about metrics in this context. Explicit solution for the metrics. So that's something that would be interesting to explore further. But we will limit ourselves to the algebraic context, and we will rely on dualities with other systems in string theory to be able to predict something, for instance, about the Higgs branch, no? And then, like, what is the metric that does the job that we want is the one which is dual to that brane system, no? If somebody has another metric that doesn't do the job that we want, then that's not the one dual to that brane system. It's another metric. It happens all the time. Think about LE spaces and Taub-Nuts. No, they are similar metrics, but one is dual to a D6 brane, the other is not. No? So what I wanted to say then, yes. So why is this interesting? Because the Higgs branch, you see, it's the complex structure model in M theory. It can receive corrections. No, it's Keller moduli we trust. No, there are no quantum corrections. Higgs branch, they are 3 cycles, calibrated 3 cycles. Euclidean M2 branes can happen, and they can modify it. So it is interesting to see if there are field theoretical methods to control this. No. So let's go here. What are the atoms? Is there a clock? No. What time is it? 26. So I have 34 minutes.
Yes.
Okay. Hey. So bribes. Okay, very good. So we'll think about it in 33 minutes. So what is the philosophy here? Well, we have these ADE singularities. They keep mentioning. I never write them. Let me write them once and for all. No, the 6 is 7 and the 8, and x squared plus y squared plus x to the n plus 1. Then there is x squared plus z y squared plus z n minus 1. X squared plus y squared plus z to the 4th. X squared plus y squared plus y z cubed, and then x squared plus y cubed plus z to the 5th equal to 0. These are the germs of these singularities. No? Okay. And they are the Duval singularities. So you can, beautiful algebraic geometry, you can take the invariant polynomials associated to these SU2 subgroups that I'm mentioning all the time, and you get these algebraic models. Now, how do you build a conformal matter of this type, an atom like this? What do you want? You want a curve of singularities of type G that meets another curve of singularity of type G in a singularity of higher rank. No? This type G, this is the CFT point. Why is that? I haven't said. No? So Coulomb branch, the rank of the Coulomb branch is given by the H4 of the resolved geometry. No? But you can compute also H2, and if you take the difference, this is the number of mass deformation, mass parameters of the CFT. And so, in particular, so this Calabi-Yau is non-compact, no? And I told you, gauge symmetry is associated to having a P1 which is compact. No? The size of the gauge group is controlled by the volume of this P1. No? So if I want to have a phenomenon where I have a global symmetry and I gauge it, then what do I want? I want a curve which is non-compact, a curve that supports the flavor symmetry, supports the mass deformations associated with this flavor symmetry, and I want to be able to make it compact at finite distance in moduli space. No? If I can do this, I have a geometry corresponding to this to the atom, and then I have a new geometry where I took two geometries of this type and I glued them together. By doing that, I have produced a finite size P1, this one, no, which supports a singularity G here. Now this one is finite size, so it's a gauge theory phase. And now I have to check whether it becomes a CFT or not. So if I can shrink this to 0 size and get a singularity which is at finite distance in moduli space. No? So this is more or less the logic behind this conformal matter idea. We start from the atoms, we start building these collisions of singularities that are just the minimal ones that have these non-compact curves of ADs. And then we bring them together in such a way that we create some regions like a gauge theory phase here with the gauge group that we want, and we check that we can go all the way to the conformal point of the molecule. Okay. So how do we construct this? Well, to construct the atoms, it's very simple. You just do a base change. So the singularity. Let's do an atom of type E. Have y cubed plus z to the 4th equal to 0, and then let's say I take x equal to uv. This is a base change operation, it's called. This is now a Calabi-Yau threefold. These were singularities in C2. Now this is a singularity in C3. No? And you see that if I look at the locus u equal to say y equal to z equal to 0, this one has a singularity of type E. And then there is another one, the locus v equal to y equal to z equal to 0. This is another singularity of type E. This is one locus, this is the other, and they meet at the origin at this singularity here. And exploiting standard techniques in singularity theory, one can check that this one is at finite distance. This is related to the structure of the scaling of these variables. No? And now one could ask, okay, so we claim if I take this geometry, I have a CFT that has a flavor symmetry which is at least E6, E6. No? So something, it's like a bifundamental but of E6 type. No? Can we check that this is the case? And one could do it, and we did it in the first paper on the subject by resorting to a gauge theory phase. We resolve the singularity. And you see, like what I mentioned before, that there are these loci where the instanton can become tensionless. No? When that happens, it can happen that maybe in this region you have a description in terms of a given gauge theory, A, and then far away in the Keller cone, there is another region, say here, for instance, where you can describe it using a gauge theory of a different type. No? When this happens, we say that the two theories are dual in 5 dimensions. No? But let me stress that the duality in 5 dimensions is a very weird notion, no? Because we are used to, like, a sensible notion of duality is that there are two things in the UV that flow to the same infrared point, no? Because no matter what I do, at the end, when there is the thermal death, we flow to the same place, no? Yeah, exactly. One takes you to one gauge theory phase, one takes you to another, no? And then, if you were a low energy person that just started with the gauge theory, you would think I have a different gauge theory, no? But then, really, secretly, they are just two different relevant deformations of the same conformal point. And then, when that happens, we say these are dual, no? So that's useful because, like, we start from this molecule. It looks very non-Lagrangian, no? It has a E6 times E6 symmetry. It's insane. But let's look at some resolution here. We resolved it. And there is a specific resolution of that geometry where it gives rise to a quiver gauge theory phase, an ordinary quiver gauge theory phase. Has a description in terms of an E6 quiver with SU2 ranks 2, 4, 6, 3, 4, and 2, with a global symmetry here, which is of rank 1. No? So there is this theory here, this E6 atom, admits a gauge theory phase of this kind. And Tachikawa, and also Yonekura later, in same 15, both of them, they show that if you have a 5D quiver gauge theory, special unitary quiver gauge theory, of shape G, which is balanced, then there is flavor symmetry enhancement. There is a flavor enhancement precisely to a flavor symmetry that is at least G times G. No? So this is the case in our case. This is an E6 quiver. Balanced means that you take twice the gauge rank and you subtract the gauge ranks on the neighboring nodes or the flavor symmetry and you get 0. So for instance, 4 times 2 is 8 is equal to 2 plus 6. 6 times 2 is 12 is 4 plus 4 plus 3 plus 1. No, this is balancing. No? This is a condition on the quiver. So whenever you have a quiver that has a G shape and it is balanced, then these gentlemen show you that you have the flavor enhancement that you want. So even from the gauge theory phase perspective, this theory indeed has E6 flavor symmetry. No? So yes, we checked it. It works. Moreover, you see, I told you this molecule is a molecule of type X because I use X to do the base change. And for free, I get other molecules. I get a molecule of type Y, UV, and a molecule of type Z, UV. By performing these other base changes, I get different geometries. And they give rise to different types of atoms. No? So there are atoms of different types already. So same type. Let's say, more atoms. There are more atoms of the same type. Okay. So the type, remember, is the flavor symmetry. So this is E6, no? And this is one atom of type E66, and then there are two more, no? One with this base change and one with that base change. No? These are three different geometries. X equal to UV, Y equal to UV, and Z equal to UV. There are three different types of atoms of type C6. And then similarly, you just play the same game with all the AD series, and you get three different types of atoms for free, for all of them. And for all of them, we find gauge theory phases of this type, and exploiting the Yonekura-Tachikawa criterion, we show that they have a flavor enhancement, so that's good, no? And then, can we form the molecules? Can we do something like a molecule out of those? That's very, very nice, because you see, if I want just two copies of this type, that corresponds to just raising this power, to the second power. No? Second power here corresponds to taking two conformal matter and gauging the common G. And you can do that. You can show, by resolving this singularity, you can show that there is a generalized gauge theory phase of this kind. But there is also a generalized quiver gauge theory phase where you multiply, say you take n copies here, and you multiply this by n. Okay? And so you have so here you would have n nodes of type G. Sorry. Okay, so there are n nodes of type G. And we have an example of a new 5D gauge theory duality. There is a linear quiver where all the gauge nodes are exceptional now, and the matter is by fundamental links of this atomic type, an A-type AN quiver, linear. And it is dual to an E6 quiver with complicated gauge ranks that somehow remember about the number of conformal matters that enter, no? And because of the Tachikawa Yonekura quiver enhancement, we see that so there is this G times G enhancement that we want. Moreover, like if you think about it, you realize that essentially you can form more general molecules just by taking, say, Y to the K and Z to the M, no? And this is a molecule where I have n copies of the first type, k copies of the second type, and m copies of the third type. I can form a linear quiver much more complicated. And again, there is a way of reading off a quiver gauge theory which is balanced and everything works. So very, very good. It seems it works. We have a story. Are these all? No? Are these all of them? No? This was the question that we ended up last time. And like there are for all of these models, there are these new dualities. And so one could ask, well, what is this, so the Yonekura-Tachikawa criterion, no, just requires the quiver to be balanced, no? So why don't I start thinking about it, no? I take a type, I take a type E quiver like this, no? I put arbitrary flavor ranks here, no? F1, F2, and so on, no? And of course, like most of these guys, no, are not minimal. They are not going to be atoms, no? I expect I expect to have some condition about the fact that the various ranks of the gauge groups in the SU quiver gauge theory phase have to be coprime, no, for atoms. That makes sense somehow, no? And indeed, one can look into this, and the balanced condition what quivers of G shape are balanced. This is a theoretic question. No, it's a question about the structure of the weights, certain specific weights. No, because the condition here that the quiver is balanced is essentially a condition that it is an eigenvalue of the Cartan matrix, no, of a specific type, and then you can just ask the question in the context of the root lattice, where it is easy to answer, no? And we find an answer, no? And everything is determined in terms of specific subcollection of co-weights, no? There is a specific that for type G conjecturally determines the atoms, no? The reason why we expect that they determine all atoms is because if you have a gauge theory phase like this, then you can establish a hierarchy between your model just by usual standard Higgsing. You know that you can Higgs down, and that means that there is a hierarchy between these models. No? And this hierarchy is the hierarchy that we use to identify the specific collection of minimal co-weights. So, for example, no, if we start from again using the E6 theory as our example, no? So, if you take, for instance, the co-weight 1, 0, 0, 0, 0, 0, no? So this one, the co-weight determines the rank of the flavor symmetry and the rank of the gauge nodes just by applying an inverse Cartan matrix. And so in this case, the quiver gauge theory phase is a co-weight. This is the gauge theory phase. And this is the base change. And this is type E6, okay? So in this case, the gauge theory phase is this one, 1, 2, 3, 2, 1, 2, and then there is a global U1 here. And then the base change here is a Z cut, so UV. And then you go on, there is the 1, 0, 0, 0, 1, 0. And this one is the one that we've seen before, 2, 3, 4, 3, 2, 2, and then 1, 1 global. These 1, 1 global are these global flavor symmetries, and this one is the Y cut. And then you go on, and there is, say, 0, 0, 0, 1, 0, 0, 2, 4, 6, 3, 4, 2, 1. This is the X cut. So this is the gauge theory phase that we've seen before, no? And now you know what are the gauge theory phases for all of them. So for X, Y, and Z. And if you form a molecule, then the structure of the gauge theory phase will be just add, according to the multiplicity of these variables, you just add to the dimension vector, this dimension vector times that multiplicity. And then one asks, are there more? Yes, of course there are more. So for instance, there is the 3, 0, 0, 0, 0, 0. And this one corresponds to a gauge theory phase of this type. This one is balanced. Is there a corresponding geometry? And with hard work, we found that there is a fine-tuned geometry with this type of cut. So this is the base change that give rise to this resolution. Yes.
That was very fast. Every time you talk about this base change, it seems you always want to do it at the superconformal point, at the secret point. But the moment you talk about gauge theory phases, you're actually resolving this.
Yes.
And you said that all of these things are supposed to be connected. So
yes.
Why in the world would you only expect?
Exactly.
Base changes
just
that happen at the superconformal.
And indeed, yes, exactly. Yes, that was a very good remark. Yes.
Another question is,
yes.
When you're resolving this gauge theory phase, you're going to introduce some complex parameters, I suppose.
Yes.
Okay. So then those complex parameters, what's the gauge theory interpretation?
This would give rise to I will speak about it later if I manage to bribe her high enough. but the idea is that along the gauge theory phase in this cone that I erased, no, there is a Higgs branch, and those complex structure moduli that respects it are the Higgs branch of that gauge theory. No. However, if you zoom down to the singularity, there can be an enhancement And the Higgs branch that you see from the gauge theory point is not the whole Higgs branch of the field theory of the CFT. There is a larger moduli space that you have access to only from the CFT point, and that indeed matches. And you see, like, and then, okay, there are there are 3 more atoms. No? And then, on top of that, we find that there are some other weird collections of weights that also have this correspondence, which we call hybrids. So an example of an hybrid is like this, 0, 1, 0, 0, 1, 0. This one has a quiver gauge theory phase of this type, 3, 4, 8, 4, and then 6, 3, and then 1, 1 here. And also this one has a base change, weird type, so it's something like x dqcy squared equal to uv. No? Very, very weird. No? Also one parameter. This is freely tunable parameter. One of these complex structures that we were mentioning. So this one is a hybrid. Why it is a hybrid? Because it behaves like an atom, so you can form molecules with it, and there is no E6 gauge group within it, so in the gauge theory phase, so we treat it as an atom. However, it can be Higgsed. Can be Higgsed to a theory of this type, like 3, 5, 7, 4, 5, 3, and then 1, 1. And this one is a molecule. It's a molecule that you would obtain if you take like E6 here, global, take a matter of type Z, gauge it with an E6, and matter of type Y, and then gauge it with another E6. So you see that Zy, Z is here, Y is there, no? And by combining them, you find the right dimension vector. Here there is a 1, no? So 2 and 2 is 4, 3 and 4 is 7, 2 and 3 is 5, the flavor symmetry just combine, no? And so you have an atom, so something that looks like an atom, a minimal theory, but that one can be Higgsed down to a molecule, okay? So in this hierarchy, by Higgsing, one finds that there are genuine atoms like this, that are organized like this, but there are also some hybrids that are like, they behave like atoms, so you can form molecules with them, but they also can be Higgsed down to some molecules. So they don't really respect this hierarchy. But the main result that I want to advertise, so this is for the E6 case, but we did it for all of them, no? But because the point is indeed classification, no? So the main insight is that for all of these Yonekura Tachikawa balanced quivers, there is an algorithm that gives me a geometry, a singular geometry. So all quivers that have the requirements to be interpreted as atoms, meaning that they sit at the bottom of a Higgsing tree, no? All of them, now they have a geometry. So they give rise to CFTs. They are not just naive effective field theories that maybe have some subtleties. No, we have a geometry, a concrete Calabi-Yau geometry that has that gauge theory phase. No? And then, by combining them, forming these generalized linear quivers, we predict a zillion of new 5D dualities, no? Because we have all the ones that you obtain by forming molecules out of these atoms and these hybrids, and all the possible gauge theories of type E, suitably balanced. No? So we can recover all of them, and they all fit in a nice global framework. No, it fits. Now, how many minutes do I have?
Well, I haven't received the bride yet, so you have 9.
9 minutes. Okay, maybe I won't need to pay you after all, with the relief of all the participants. So what about the Higgs branch? What about the Higgs branch? Quickly, because this is more or less standardish. What about the Higgs branch? So there are two different stories. There is a story for atoms, and there is a story for molecules. Okay. So the logic is always the same. We have a 5D theory. No? We perform a circle reduction. We obtain a 4D theory. And then we also have a dual description in terms of a web of PQ5 branes. This is a dual for G equal to A and D. No? This one is always true. And what can we say about these theories? And out of this, what can we say about the Higgs branch? So this one, by standard techniques, give rise to description of the Higgs branch from the so-called magnetic quivers. Okay. Here, from geometry, we have the Chi structure deformation. Okay. Complex structure deformation from geometry. Magnetic quiver from the PQ web. And then, in some cases, we know what is the 4D equal to 2 theory we land on. And in that case, we can use the fact that the Higgs branch does not receive corrections. And we can use the 4D equal to 2 tools to compute the Higgs branch, and it will match with the one above. No? So for the atoms, this strategy works very well. For the atoms, we have a situation where we have this 5D moduli space. No? There is a super conformal point here, and then you can think of going to the quiver gauge theory phase here. No? And the circle reduction here under S1, we obtain a 4D KK moduli space. Here at the origin, we have a classes theory. And so if you have an atom of type G, and then some other label associated to the base change, let's call it W, then we have a classes theory here that becomes a fixture which has punctures of type G, carry flexibility G and G, and then here we have a third type of puncture which is associated to the base change corresponding to the atom. No? And then there is this deformation here. And we have another point on the Coulomb phase where we have the 4D quiver, which is just the circle reduction, if you like, of the gauge theory phase. No, these two are not the same theory, no, because this is a relevant deformation. Relevant deformations and circle reductions, they don't commute. So this is a quiver gauge theory phase in 4 dimensions, a different theory. The circle reduction here give rise to a CFT, and this CFT is really the CFT associated to the circle reduction of the 5-dimensional theory. No? So in this case, we have techniques, class S techniques, to compute the dimension of the Higgs branch in terms of the structure of the puncture. No? We can compute the dimension of the Higgs branch. And then exploiting these magnetic quiver techniques, we can obtain a different description of the same Higgs branch. They match, so we are happy. And they match also with the counting of complex structure deformations. For the molecules, the story I told you is different. Yes? No. Or maybe there is, but not that we haven't studied it. Like this is like this. If you think about it, this is the Coulomb branch moduli, if you like, of the 4D Kaluza-Klein reduced theory. So there's a lot of funky stuff that can happen. They are not. They would not be related as 4D theories. They are related as different ways of decoupling the KK towers. No? For the molecules, the idea is that we have a theory here, the 5D CFT here, with the molecule. There is one quiver gauge theory description in terms of the quiver gauge theory phase that we discussed, the Tachikawa-Yonekura quivers. But then there is another gauge theory phase, let's call it Q tilde, where we have a quiver, the conformal matter quiver. And now, if you go down on the circle to the 4DKK space, this one will have a class S construction. It's just obtained by taking as many copies as we want of the given class S theories, labeled by the same punctures associated to the atom, and then performing the fixture. So this is a G-type gauging, no? As a 4D n equal to 2 theory. So this is a 4D n equal to 2 class S. This is associated to the circle reduction of this quiver gauge theory. Then there is another one here, which is the 4D quiver. But then we don't know what is like these are related. They are associated with 4D KK space. But then there is a different theory associated with circle reduction of the molecule. It must be a 4D CFT because like you just restrict to the lowest lambda O level of the Kaluza-Klein tower associated to the circle reduction. You started from a CFT, you must land on a CFT. No? Scale invariant goes to scale invariant. We don't know what it is. Like we can compute some properties of it. We know what is its rank, what is flavor symmetry. But for instance, we don't know what are its Coulomb branch dimensions. We know that the rank is high. Like one of the features of this construction of conformal matter is that often to classify 5D theories, people work it with low rank, do some gauge theory computation, no? Start colliding divisors, gluing them together. No, we have a quiver technique. So we can produce systematically huge classes of models, no? And predict their properties. And so here, like, however, exploiting the magnetic quiver, this magnetic quiver, we can compute the magnetic quiver in this phase. We can compute the magnetic quiver in this phase, and we can compute the magnetic quiver in this phase. And using the geometry, we can compute the complex structure moduli that preserves this quiver, or this quiver, or the conformal point. And in those cases, there is a matching. No? So this is a non-trivial result. It means that really the magnetic quiver somehow informs about the complex structure moduli of a theory. Which is I think it's an interesting result. 1 minute. I can give you my yellow chalk. Minus 30 seconds. Oh my god. Okay, so it's done. Wait. Maybe if you want to hear about the trinions, maybe you can ask it during the questions.
Well, I was a little bit nasty, so now we have plenty of time for questions. Any questions? So you had a question for yourself, didn't you?
I wonder if these 5D conformal matter theories admit trinions. Oh my god, what an interesting question. In fact, that's the topic of our next project. No, seriously, if you want to hear about it, I can speak briefly about the trinions. But I have 2 minutes, okay. So this whole story was about building linear quivers, like by matter that was 5D conformal matter that was bifundamental like, no? We formed these linear quivers that are essentially the 5D version of these fixtures, no? But one could ask, is there a way of building quivers which are more general, like this, where we have now trivalent vertices, and maybe we can give them genus, no? If we do something like this, no? Maybe like this, no? Yes, this is more like it, no? And something like this. So is there something like this in 5 dimensions? In 4-dimensional class S, we have it, no? In 4 dimensions, these are the TN theories, no? And we know that we can form these generalized quivers. These are SUN or whatever G-type symmetry. You can do it, no? So in 5 dimensions, naively, we can do it as well, because just think about the singularity C3 mod Zn times Zn, no? And this one corresponds is dual in the PQWeb construction to a collection of 5 branes and of NS and D type that meet together. And here we have an SUN global symmetry. Here we have another SUN global symmetry. Here we have another SUN global symmetry. And we can glue them together by means of toric geometry. So we just do something like this. And we know what is the dual toric threefold, just because here we have some non-compact singularities. And the process that we have is indeed just like making them compact, no? Are you familiar with this language, more or less? No? So the idea is that each patch is a patch of this type of singularity, and by gluing them together, we find that now this curve corresponds to a compact curve. It's not on the boundary, so it's compact, and this corresponds to gauging the global symmetry. So naively, one would say, okay, of course, it's in toric world, we have the trinions. Also, the tetraons, we can do things with 4 flavor symmetry, pentatons, whatever. Like, you can go on and find. But there is an atomic classification with trinions in the class S of type A. They have an uplift in 5 dimensions. So the question is, how about D and E types? So with a lot of effort, we find trinions of D type, for instance, like a geometry of this kind. This is the D type singularity. But now we have a different type of base change. And this one gives rise to a configuration where we have a collision of D-type singularities, of 3 of them. So naively, if I were to represent it as a generalized quiver nodes, I would say dk, and D2j, something like that. No? This looks like a trinion. But by studying the resolution of the singularity, we find that it is not an atom. So in the type A cases, they were atoms in all respects. So they don't have gauge theory groups of type SUN. But the D types, they have a gauge theory phase, where essentially they can be described all in terms of a linear quiver with D-type conformal matter of D2J, whatever. No? And then on this node, we just gauge 2 new fundamental theories now. And so we see that we have just introducing these 2 new theories, we can cover all the trinions. We have, looking for the trinion, we just discover 2 new atoms. That's it. With this, we can recover all these singularities, all these trinion theories. And we see that the chemistry of the trinion just comes from the chemistry of the conformal matter. It's just this tail, which is built out of the conformal matter that we have before. We can make it as long as we want, no? And and this is a quiver of decay shape, no? So yes, and just exploiting these 2 atoms. So this is as far as the trinions, no? We have these ones, and then there are we have we can form something like with 4 flavors of type D, 3 flavors of type D, 1A, 2Ds, and then E and 2Ds, and that's it. But there are no trinions with exceptional gauge groups. So that's a bit of a puzzle. No, why can we do it with the D type and we cannot do it with the E type? And why do these have such a different chemistry? You know, with the A type we can form all the classes theories, all these networks, etc. With the D type we just can elongate them at will. But why not with the E type? What's wrong with the exceptionals? And if you think about it, there is a conjecture about the origin of all higher dimensional CFTs from 6 dimensions, as from reduction, toroidal reduction, circle reductions, compactification of Riemann surfaces, etc. And in the atomic classification of 61,0 theories, the maximal exceptional flavor group that one can find is E8 times E8. And there is no way of fitting 3 copies of E6 inside E8 times E8. So somehow, like the difficulty that we face in the geometric construction of the trinion, of the exceptional trinions, might be interpreted as an evidence of this conjecture about the 6-dimensional origin of all theories. Because if one could construct a 5D theory that has this flavor symmetry, then it would be hard to just obtain it from 61,0 from circle reduction. Of course, like we are in the process of trying to find a geometric argument that would forbid that. No, if you can prove that, in most of the cases we can exclude that we can form trinions of this type because we try to collide these singularities and we obtain a singularity that cannot be at finite distance. No, and so the question is like, is our geometric model generic enough? Can we really rule it out or not? And this is the real end of my talk. Thank you very much. Yes.
Just to understand the argument, like the three quarters of AN are also not inside the A times A define big enough.
Yes, but you see, like it's not you can form in 6 dimension SU to whatever rank times SU to whatever rank, and there you can fit 3 copies of SU, no? But you cannot fit E in type A.
I don't understand why this a kind of 5DKN theory cannot be decomposed into a SN, because I think maybe if you draw this internal of this triangle as a track diagram, it's immediately split into a chain of straight partition functions which correspond to a chain of SUN and so on.
It's true, yes. It's true. Like, but the point is that is in definition of the type of the atom, no? So when you have this TN theory, no, the idea is that it has a quiver gauge theory phase, which is essentially very natural from the structure of the toric diagram. So it has the structure of, say, 1, 2, 3, 4, n minus 1. These are gauge nodes. And then there is a global n, no? And you see, this one is an atom. We would say it's an atom of type SUN, n, cubed. And there is no SUN gauge group in the gauge theory phase, no? So there are all the way up to rank n minus 1, but not the one associated to the type, no? Yes. Somehow. But the idea is that from this gauge theory phase, if you use this Tachikawa-Yonekura enhancement, you will find out that on top of this SUN, you have an enhancement to SUN times SUN, no? By the same reasoning. So this is an A case of that same logic. No? So eventually you end up with SUN cubed global symmetry. Yes.
Do you have any idea of how, like, a mirror to these geometries?
A very good question. It would be another way to tackle this for DKK reduction. We haven't thought about it, but in some cases I expect the standard techniques should, especially when you have a Landau-Ginzburg type description, should be able to derive this type 2B version of these geometries, but we haven't looked into it. Yes. No. No guess. It will have a gauge theory phase in terms of these classes theories, plus these two satellites, which are probably some DPG type theories in the circle reduction. No, but I don't know exactly the details. Yes, and especially we don't know what is the direct circle reduction, the one that doesn't go through the gauge theory phase. Yes.